Dr. Ho?
Yes.
I think I'm first up in this next group. Do I wait?
Yeah, Dr. Marlik is the chair, and then she's going to introduce you.
Okay, great, thank you.
So good morning. I think it's already 10:30 at your place. Am I right?
Yes, yes. Go ahead.
Okay. So now we are going to start with the next session, and this session is of contributed talks, and this is session 1. And the timing is from 10:30 a.m. to 11:30 a.m. And here we have 3 talks in this particular session. So to start with, we are having Professor Douglas L. Strout with us. And let me give a very brief introduction. And the reason is, it's not that he's having a brief introduction, it's a long one. But since I could find only few things, so Prof, please don't mind it, right? Okay, so he is a professor of chemistry at Alabama State University, having a pretty long experience of more than 21 years. That is, he joined since August 1999. And before that, he worked as a postdoc at Pacific Northwest National Laboratory and Texas A&M University. He completed his PhD from Rice University and BS in Chemistry and Physics from Texas Christian University. He is specialized in physical chemistry and computational chemistry. He trains students for careers in research, forensic science, medicine, pharmacy, etc. He has a long list of publications which have been published in various international journals of repute. And today he is going to give a talk on binding of high energy N4C2 to first row transition metal atoms and ions. So over to you, Professor.
Okay.
And your time starts now.
Thank you. Let me get my screen share up and running here.
Yeah, I'm just quitting it so that you can join. Yes.
Am I good?
Yeah. Just go on the screen, full screen.
Okay.
Go on the screen show, it will be fine.
Oh, like that then?
Perfect.
Okay, great, thank you. Okay, thanks first of all to Dr. Ho and Dr. Ho especially and the organizing committee. I think there'll be no doubt that by the end of this 2-day symposium, the final score will be Symposium 1, COVID 0. And it's somewhat fitting that we're all viewing this talk of mine on a computer, because that's basically what my work is. My work is computational in nature. The chemistry I'm going to be discussing is computationally modeled, and no, I did not in fact synthesize any of the molecules I'm going to discuss. But let's look at the basic idea. Our basic idea is high energy nitrogen, that complex forms of nitrogen are highly energetic for basically one very simple chemical reason, that complex forms of nitrogen decompose into N2, which is a very, very exothermic reaction, mainly owing to the strength of the nitrogen-nitrogen triple bond. On the plus side, since the sole product of this of reactions of this kind is N2, which is 80% of the atmosphere we're all breathing already, You know, there's also an aspect of environmental friendliness to high energy nitrogen. Here's the difficulty, though. A number of these nitrogen forms have been synthesized, but there is a stability issue. There is a stability issue. If a molecule is highly energetic, but it decomposes too easily, then that's going to be a problem. That's going to be a hindrance to technological applications. I mean, I was at a conference some number of years ago, listening to a talk given by someone that was in the synthetic field, creating molecules of this kind. And what made an impression on me is one of the photographs he showed during his talk, where he was showing, it was a picture of nothing but an NMR sample tube, one end of which had been completely sheared off because the sample he was trying to analyze detonated in the tube. A basic situation I think we could all relate to is the gasoline in our cars. Doesn't the gasoline in our cars wait for us to ignite it before it starts burning? And don't we all sleep real well at night knowing that? That's stability. An energy source is a high energy source is of more practical application if it is stable enough to wait for you to ignite it before it starts releasing energy. That's you know, in basic what I'm talking about. A possible solution to that is, instead of having the molecules be 100% nitrogen in composition, incorporate other atoms into the structure to stabilize them while still maintaining a desirably high mass contribution from the nitrogen. So let's take a look at something we've worked on in my lab in the past. And that's a molecule goes by the chemical formula N4C2, pictured on this slide. The nitrogens are yellow, the carbons are black. Molecule has a kind of an intermediate molecular mass, 80 grams per mole, is not 100% nitrogen, obviously, because of the carbon. But 70% of the nitrogen, 70% of the mass is still nitrogen. So it's still predominantly nitrogen. We characterized this with a set of theoretical calculations some time ago. The citation is on the screen. And our conclusion from that study is that all reasonable dissociation pathways for this molecule are high in energy. They're high in energetic cost, meaning that the molecule would require a significant activation energy, a significant ignition to it, in order for it to decompose. And that, you know, at the time we claimed that was a good thing for stability for a high energy molecule. So we'll look at this question. If this molecule could be synthesized in bulk, how would you store it? My thinking is just on basic, fundamental, just, you know, real first level chemistry. This molecule has a mass of 80. It's nonpolar, which would make it comparable to other molecules, say, you know, benzene or cyclohexane, you know, molecules that our students would have had some experience with. And those molecules are liquid at room temperature. If let's say you wanted to store this material in the solid state, you might need to do something else with it. For example, bind the N4C2 to metal atoms. It would add significant weight and make it easier to store these molecules as solids, if that were desirable from an application standpoint. Which leads to a fairly straightforward and obvious question: does this N4C2 bind to metal atoms? Does it? I mean, we need to know that. Okay. So how do I go about, in this research, how do I go about trying to figure that out? Our computational tools and methodology are listed on screen. We're using density functional theory and the atomic orbital basis sets for Tom Dunning. My intro was said I was at Pacific Northwest National Laboratory. Dunning was my mentor. So personal bias, I use the Dunning basis sets in my work now. Here's our methodology. Here's how we're going to do it. Here's the meat of what I'm doing here. I'm going to estimate by theoretical models. I'm going to estimate an average metal to carbonyl binding energy. Carbonyl is a classic. Carbonyl is a classic ligand in transition metal chemistry. It's well known. It's well characterized. And I'm going to use carbonyl as a basis for comparison to judge the behavior of N4C2. So I'm going to calculate average binding energies of metal to carbonyl, CO. And then I'm going to calculate a substitution energy, just a one ligand for one ligand swap out between carbonyl and N4C2. And in fact, you see one of the results in my picture here. This is a metal atom. What's shown on the screen is a metal atom with 3 carbonyl ligands. The COs are black and red, and the N4C2 is black and yellow. And then once I have the carbonyl binding energy and I have the substitution energy for N4C2, I combine those two results to estimate the metal to N4C2 binding energy. So let's go on to some results. What you're seeing here is computational estimates of the average binding energy of the carbonyl ligand to a number of first row atoms and ions. I'm using atoms of iron, nickel, zinc, and their double plus ions. And what this table is showing, this is our computational estimate for the average carbonyl binding energy, which actually is negative in the case of zinc 0, meaning that dissociation of the carbonyl ligands from zinc 0 would on a net basis actually be exothermic. The binding energy there is actually less than 0. So each of these, this is the metal to carbonyl binding energy. That's what you're looking at on screen now. And then what we're going to do is we're going to take this average energy, the energy per carbonyl, the farthest right-hand column on the screen, and then we're going to add that. We're going to take those results and add them to the results on the next slide. N4C2 versus carbonyl substitution energy. In other words, which is a stronger binder of the metal atom, carbonyl or N4C2? I have the 6 results for the metal atoms and ions from the previous slide, and in 4 out of the 6 cases, it looks like 4 out of the 6 cases, the N4C2 actually is a stronger binder than carbonyl is to the metal center. Iron 0 and nickel 0 being the exceptions. The positive numbers on this slide indicate greater strength of binding by N4C2 relative to carbonyl. The negative numbers indicate that carbonyl is the stronger binding ligand. So if we take those two, if we take that slide, if we take this slide's results and previous, we move to the summary slide. Oh, hello. There we go. And what you see here, what you see on screen now, is a combination of the results from the 2 previous slides, where I'm listing the metal carbonyl binding and the substitution energy. And if I add those 2 results together, what I obtain is an estimate of the binding strength of N4C2 as a ligand to the metal atoms and ions. And what we are seeing in all cases, is that the metal ion, that the atoms and ions bind N4C2 at a strength of approximately 100 kilojoules per mole regarding the charge 0 atoms, and several hundred kilojoules per mole regarding the double plus ions. So what do we conclude from that? That the N4C2 ligand binds more strongly to the metal ions than to the metal atoms. I don't think that's too surprising because you would expect the CN triple bond on either end of the N4C2 to polarize the nitrogen atom negative, which would make it a stronger binder to a positive ion as opposed to a charge 0 atom. So I don't think that's too surprising. Regarding the metal ions, N4C2 actually bonds more strongly than carbonyl does. And carbonyl, like I said before, is a classic, well-known, well-characterized ligand. So if carbonyl is a well-characterized ligand that forms stable complexes, is actually outperformed in terms of bonding strength by the N4C2 ligand, then my final conclusion is that N4C2 should be able to form stable complexes with the metal ions in question. So in other words, what I'm saying is, to answer the question from a number of slides ago, does this ligand actually bond effectively? And could it be used, could metals be used as a storage, potential storage medium for high energy N4C2? My claim is, based on these results, that the answer to that question is yes. That there is significant bonding strength, and we could synthesize, it should be possible to synthesize stable complexes of this kind. I'm going to give some brief acknowledgments. I'd like to give a shout out to my friends up in Huntsville at the Alabama Supercomputer Center. You know, Dave Young and the people up there do a great job, and using their facility. They have some great facilities. They have some great facilities. We get a lot of good work done using the resources up at Huntsville. And an acknowledgement of ASU's College of Science, Technology, Engineering, and Mathematics, who funded my last software upgrade here on campus. Because not only do I have access, are we able to use Gaussian 16's computational tools remotely at the Supercomputer Center, we also perform calculations right here on campus using ordinary PCs. So yeah, the computational tools are very robust, and in fact, I use them with students in my physical chemistry laboratory. So we at least get the students a taste. So I'm going to thank everybody for their time and attention, and conclude the presentation at this point.
Thank you, Professor. And in the chat box, there is a question for you from Laila Rohani. And the question is, did you treat metal ions and other atoms at the same basis using DFT?
Yes. Yeah. Short answer, yes. All of the calculations. I may have gone over the point rather quickly, but for those, for those theoretical chemistry aficionados among us, we use the Dunning polarized triple zeta basis set, which is a fairly robust basis set in terms of the atomic orbital functions that are within it. So, but yes, all atoms, the metals and the ligand atoms, were treated with the Dunning polarized triple zeta basis set.
So thank you, Professor. I think maybe the students write something more in the chat box, but right now we don't have any more questions. And so we thank you for this wonderful lecture. Very clear.
Okay.
So.
All right, I just took my screen share down.
Yeah. So the next lecture is from me. So I think I have to introduce myself. It's okay, no problem. Just a minute. Let me go to the screen share. And here I go. Yeah. Okay. So the next lecture I'm going to deliver on effect of illuminated nights on temporal organization of behavioral and physiological functions. So our lab is working basically on birds. So my model species here is going to be bird. And let me tell you why I have chose this particular topic. Because nowadays we are finding that light has emerged as a pollution. Light is very important, we all know it, but overuse or the use of the light at the wrong time of the day, rather night, is not fair. And if the nights are illuminated or the light has been provided during the night also, which we are seeing in the environment these days, it is really going to be fatal. And therefore, I choose to present this. And let me open my presentation. Just a minute. Just a sec. So, can you see the slide?
Yes.
Okay. Okay. So the title, as I have already told, it is Effect of Illuminated Nights on Temporal Organization of Behavioral and Physiological Functions. And this is a study on birds. And myself, Shaili Malik from Department of Zoology, University of Lucknow. So as we know that life on Earth is governed by the cyclic presence of day and night. And for billions of years, all life has relied on Earth's predictable rhythm of day and night. It's encoded in the DNA of all plants and animals. And under natural circumstances, day is illuminated by the sunlight and night are usually dark. With advancements in science and technology, the dark nights are now brightened. But how this night brightness is being taken up by nature and other life forms is a big question. So humans have radically disrupted this cycle by lightening up the night, and plants and animals depend on Earth's daily cycle of light and dark rhythm to govern life-sustaining behaviors, which may be in the form of reproduction, nourishment, sleep, and protection from predators. So artificial light at night has devastating effects on reproduction. Fatal attraction, if I'm saying fatal attraction, the example can be from many insects which are drawn to light, but artificial lights can create a fatal attraction. Declining insect populations negatively impact all species that rely on insects for food or pollination. Then sleep, obviously if we are getting light during the night, our melatonin levels are never going to reach that maximum, or they are going to be in a very basal state. So it is definitely going to hamper our sleep. Then the predators. We know that the predators use light to hunt and prey species use darkness as cover. And near cities, cloudy skies are now hundreds or even thousands of times brighter than earlier times. The effect of LAN seems, when I'm saying LAN, it means light at night, seems to be more prominent on nocturnal animals, especially the migratory birds, where most of them are nocturnal migrants. The bird migration represents enduring flights in time and space that may range from non-stop trans-hemispheric flights to days or months-long journey. And when I'm talking about all these, definitely our ecosystem is going to be disrupted. So I'm going to give all the cases based on the birds. So we are going to have a look on the study of the birds, wherein the night migratory birds, the geomagnetic compass helps in spatial mapping, hence they can locate their direction of movement. But the presence of light at night hinders the events regulating orientation and navigation, which may really prove hazardous to these night migrants. So now coming to the objective, and here is the objective 1. So it states to determine the effect of light at night on the circadian and seasonal responses in migratory bunting. And in our laboratory, the physiological mechanisms underlying effect of LAN on daily and seasonal responses in birds have been investigated. So this objective, for this objective, we have used the model species as red-headed bunting. This is a migratory bird, Palearctic Indian migratory songbird, and it overwinters in India and breeds in Southeast Europe. It is a photoperiodic species. long day breeder, and generally it breeds between April to July when the summer time is there and the